We will continue the exploration of the thermal reaction norm of sex ratio, mainly for turtles, but it can be applied to any reptile with temperature-dependent sex determination. In the first part, we have seen that we should define a model to describe the relationship between sex ratio at constant temperature and the incubation temperature. And we have two ways to fit the model: maximum likelihood or Bayesian statistics. I told you that Bayesian statistics offers a correct point of view, and we will see now what is the difference between both. We will analyze as a toy dataset sex ratio for Lepidochelys.olivacea using the R package embryogrowth. First, you must install R and RStudio because we will use it, and if you want to follow this tutorial, you will need this software. R is both a computing language but also a free software available in R project website. I will put in description all the code I use in this practical session. RStudio is a graphic user interface of an integrated development environment developed by the company POSIT. It is also free for NGO or research, and it is available in the POSIT website. If you publish results obtained using R within RStudio, you must give the version of R that you have used. RStudio version is less crucial because the statistical work is done by R. RStudio is just a graphic interface. The main piece of software is R. Now that you have R and RStudio, you must install embryogrowth package. This package has been developed by myself, Marc Gironto, to help people working about reptile development and sex ratio. It includes a set of functions to study embryo development, hatching success, temperature-dependent sex determination, for example. It can be installed from CRAN using install package embryogrowth, but generally this is not the last version. Regularly I add new options, I make some correction, sometimes of bugs, and you can always have the last version, the most recent version of embryogrowth and helpers MG packages, which is a companion package for embryogrowth, using these two lines. Again, I will put this in description. Now, let's play. You have embryogrowth package installed, and in embryogrowth, you have a database of incubation at constant temperature for all the publications that has been done so far about turtles and temperature incubation. This database can be accessed using DatabaseTSD. So first, you must load the package embryogrowth using library embryogrowth. Then you extract from DatabaseTSD all the lines with species being Lepidochelys.olivacea. This is the species we will work with. And we will keep only the lines with some individuals being sexed. We will work about sex ratio, so if there are no sexed embryos, we'll remove. So a sex must be different from NA, non-available, and different from 0. The database has approximately 60 columns of information, and you can see them using the function colnames with the Lepidochelys.olivacea object. And you see that you have 40 rows of data for Lepidochelys.olivacea. What is more important for us is the species range that we have. Using unique Lepidochelys.olivacea $RMU.2023, we have the different RMU for which we have information. We see that we have 3 RMUs with information: West Atlantic, Northeast India, and East Pacific. We will work in first example only with West Atlantic RMU. Let's extract from Lepidochelys.olivacea only the data with RMU 2023 being West Atlantic. Now, let's fit the model using maximum likelihood with the function TSD. So in TSD, you give the data frame of the data you have extracted. You say what equation I will fit. Here, we will use a flexit double star. I refer, if you don't understand what is flexit double star, in the previous video. I explained this equation, why this equation is until now the best equation to describe thermal reaction norm of sex ratio. And we will give some initial parameters: the pivotal temperature, 30 degrees approximately, we don't know exactly the true value now, and the SH and SL parameter. And remember that with flexit double star model, the sum SH plus SL is the TRT, the transitional range of temperature, the range of temperature where both sexes can be produced here with limit of 0.05 and 0.95. Then we can plot this model. Here you see the results of this data fitted using maximum likelihood. You see the data looks weird. There is a smooth transition from all males to p-value, and then an abrupt change, p-value to 100% female. Remember, this is a maximum likelihood model. And this maximum likelihood model answers a question that you don't want to be answered. You need the likelihood of the model according to the data, but the maximum likelihood model answers the likelihood of the data knowing the model. Let's see the results in Bayesian. In Bayesian, you must first define priors. The priors is what you can say about the value of parameters before to run the model. You can say that the pivotal temperature is probably around 30 degrees Celsius, as for all turtles. And you can say also that SL plus SH is probably less than 10 degrees Celsius, because the TRT generally is between 1 degree Celsius for laserback to, let's say, 6 for Cheloniamidas. So 10 is a real maximum. So we will use a Gaussian prior for pivotal temperature. We will take the prior with a normal distribution, an average of 30, standard deviation of 2. This is wide. Probably the true value will be inside this interval. And we will use a uniform priors for SL and SH because we don't have a lot of information about this value. And we will say that both SL and SH are from 0 to 10. Remember, this is degrees Celsius. So we will use these two functions to generate a first set of priors using normal distribution for P and uniform distribution for SL and SH. We keep the first line of priorsN for P, and we keep the two last lines from priorsU for SL and SH. We modify the range of uniform distribution using priors 2, 3, this is SH, SL. We say that prior 1, this is mean of uniform and mean of distribution are 0. For the same line, prior 2, this is a max of uniform distribution, and the max of distribution, we say it is 10. And we say that the average of the normal distribution for the prior of P is 30 degrees Celsius. Then our prior looks like the table at the bottom of this slide. And now we just need to run the model. The Bayesian analysis uses a Markov chain with Monte Carlo method, and we need to give some information about number of iterations that we want and what to do with these iterations. We ran 20,000 iterations after 1,000 iterations to stabilize the output. And we keep only one estimate out of 10 to limit the effect of autocorrelation. All these parameters can be adjusted. Just this is a generally good compromise. Then we run the analysis. It takes approximately 3 seconds or 5 seconds. Let's see the results for the P parameter. In this graph, we see the Markov chain of the different p-value that occurs during the 2,000 iteration, because we had 20,000, but we keep 1 out of 10. So at the end, we have 2,000 iterations. So you see the blue lines with a little movement is the possible values that p-value can take. And at the end, when you look at the distribution of the p-value, you have the posterior distribution of the p-value, the possible value that p can take. In red, at the right, you have the prior distribution. You see our prior with normal distribution with a Gaussian value with mean equal 30 and 2 for standard deviation. So the blue distribution gives you the posterior distribution of P parameter. We can do the same for SL and SH. This is the same, at left SL, at right SH, and you see the range of possible value that SL can take, the blue distribution, the blue posterior distribution at right, and SH the same. And for these two distributions, remember that the prior were uniform. This is a red curve that you see. This is uniform from 0 to 10. Okay, perfect. Now that we have run the model, we can ask what is the best estimation of P, SH, and SL. Here I ask what is the 99% of possible values that P, SH, SL can take. You see that P is relatively well known. You have 99% of chance that P is between 30.2 to 31.6. But SH is not very well known. It is between 0 and 5.5, and SL also is not very well known. It is between 1.5 and 9. So it is not very good. You can ask a more precise range of probability for the quantiles. Then you will, if you use the 50%, the range of quantiles where you have 50% of chance to have P, SH, SL, you see that P is around 30.61 to 31. You have 50% of chance that P is within this range. SH from 0.6 to 2.6. SL 2.6 to 4.8. So, in conclusion, you know relatively well P, but you don't know very well SL and SH, so the TRT. It is possible to visualize the posterior predictive TSD pattern using this command, and you see that contrary to the maximum likelihood, this pattern looks better. This pattern describes clearly that you have huge uncertainty for the highest part of the graph, but also the lowest. In conclusion, we have seen how to estimate the population equivalent of the thermal reaction norm for sex ratio using a flexit double star model with Lepidochelys.olivacea from West Atlantic data. We have seen that the maximum likelihood model was not correct because it shows only one particular solution, not the range of possible solutions. The Bayesian model offers more correct solution and can be directly interpreted as what is the probability that the value is from one value to the other. This is not the case for maximum likelihood, contrary to what many persons think. We have seen that the pivotal temperature could be correctly determined using Bayesian model with good precision, but not the TRT because lack of data. And the same conclusion as in the previous video, it is important to remember that this pattern must not be used to estimate sex ratio from the field. The sex ratio thermal reaction norm only works for constant incubation temperature. So you can ask, but okay, why you are playing with this if we cannot estimate sex ratio from the field? Okay, we will do. This is the first step. We will use this pattern to convert time series of temperature from the field into something that we can use with this pattern. But this is not the average value, this is of temperature, this is much more complicated. We will see in the two videos. In the next video, I will show you how we can compare if two patterns are similar or not. You remember, for Lepidochelys.olivacea, we had 3 RMUs, and we will estimate if these if the 3 thermal reaction norm of sex ratio are similar or not. See you.